Good evening, Professor.
Hello. All right. Okay. Well, welcome everyone. Welcome back.
Hello.
Hopefully you've had a productive and restful weekend, if those two things can go together. All right. Well, we are on the end of our semester. We're almost halfway through our last week together of classes. And I did just send out a message not too long ago, extending the deadline for our lab that was due over the weekend, just to make sure that everyone has a little bit more time to work on getting that in. So if you couldn't quite get it done because of other commitments over the weekend, you've got a little reprieve. So take a look at that. The problem is that now everything's starting to come due at the same time, because we don't have anywhere to go, right? We're running out of days. So take a look at that recent announcement with some reminders and that extension for the lab this week. Okay, so we have on our schedule more things than is probably reasonable. So we're going to work on chapter 13, making a good start on that. We'll definitely finish that up tomorrow. But I want to get a good amount of it under our belt, so we'll not dally too much longer, and hopefully our friends will all be here soon. Hopefully we'll have time to work on problem set 12 for at least a little bit together today. We'll see how far we get though. Okay. All right, my friends. So chapter 13, I'm going to give you a job to do as we get started here, is really kind of keep an eye out for all the different parts of our semester that are going to just keep showing up in chapter 13. There's going to be quite a bit going on here, so it's a nice chapter to kind of bring a lot of topics kind of to the front of our brains again, so that we can start that review process for our final exam. Chapter 13 kind of naturally helps us to kind of hit on a lot of those topics as we go along. And the first of them is this slide right here. So I don't know how many of you recognize it. This is from our first day of class. Our very first time together, we looked at classifying matter. And we have been focusing on A lot of the pure substances, we've been focused on the elements and the compounds and how they get put together and what their structure is, and dealing with moles and reactions. And we've done all of that with our pure substances. And we've barely talked about mixtures. We talked about them a little bit when we talked about molarity, being a mixture of something dissolved in typically water. But chapter 13 lets us start our conversation about mixtures, which is where most of the interesting stuff is anyways. So we'll work on our homogeneous and our heterogeneous mixtures. Okay. So solutions, that's when we talked about molarity and making solutions and working with solutions and using them to do stoichiometry calculations. But we had started with that idea that a solution is really just a homogeneous mixture. And our heterogeneous mixtures, those were the things that were not sort of uniform looking all throughout. Another word for them is more or less suspensions, right? So we've got different phases kind of suspended or next to each other, but they're not really uniformly mixed. There's definitely different regions, or phases is our word for that, of different materials that we can sort of visually inspect. We can kind of see that with our eyes. There is a middle ground though, in between these, in between things that are uniformly mixed and things that are kind of lumpy and chunky. We've always got that gray area in between, and those are colloids. That's the last section of chapter 13 that we're really not going to get into, but I just want you to be aware that there's this whole kind of range of ways of things to be mixed. So although we've kind of divided them into homogeneous and heterogeneous, there's a lot of things that are right there in the middle. So our solutions are things that we have been thinking of sort of on the extreme end there for being homogeneous, are things where the solute is very tiny. So less than a nanometer, right? So down at that almost the molecular size scale. So we're not going to be able to see those. So it's going to appear uniform, mixed throughout. So vinegar, like we played with over the weekend. Mineral water, it's water with all those lovely little ions and minerals and flavorings in there. Those are things that are going to look like one material all the way throughout. At the other end, right, our suspensions, we could see things. So our solutes are on the size scale of thousands of nanometers, right? They're bigger than that. So we can see them. So oil and water, right? You can see the droplets of oil. Even if you shake it, you can still see them in there. Or mud and water. Again, you can kind of get them to mix or kind of suspend and float in each other. But again, you can see that there's different regions there. And then of course, there's the middle ground, right? The middle ground where our solutes are kind of not really on the tiny molecular scale, but not really big enough for us to necessarily see with our eyeballs. So they're going to tend to be, they might look uniform throughout, but they're typically cloudy or opaque. You can't see through them. They scatter light. So things like gelatin, jello, blood, right? Which again appears uniform from our eyeballs point of view, but once you put it under the microscope, you can see that there are definitely different phases or different materials, different components in it, or fog even, with water droplets being not dispersed fully and homogeneously. Okay. So again, we are, that is, colloids are in section 13.8 of our textbook. That's not something we're going to worry about for our exam, for our course at all. Okay, so don't be alarmed that you didn't have to read that section when we did our preparation guides. But we're going to focus on the solutions part here. So chapter 13 is really going to narrow in on those solutions, right? Sort of how they're formed. We'll look at them from an energetics point of view and a molecular point of view. And then we'll look at some of their properties. So we'll work our way back up to the macroscopic scale. All right, so you can probably already see we've talked about lots of things from the whole semester. But it is time to figure out now why. Now it's time for those 3-year-old questions. Why do we even have solutions? What is it that makes them mix together? And we have 2 things going on here. One is disorder, which is around us all the time. And the other is energy. These are our 2 driving forces here that are going to make our solutions possible and probable. So we'll start with disorder, might be something we are familiar with. The science word for that is entropy. It's a measure of how random or how mixed up things can be. And disorder is the natural state of things. All right, so now you have a reason why the floor of your closet is a mess. It's nature. This is nature's way. There's a lot of ways to be messy and very few ways to be neat. So nature is favoring that sense of disorder. And mixtures, our solutions, are definitely more disordered than if we have separated our solute and our solvent. There are very few ways to keep them separate, but there's an awful lot of ways that those molecules can be all mingled and distributed as they're all mixed up together. So entropy definitely favors forming a solution. But we've also got another factor to think about, and that's energy. Again, you know, we're lazy. Nature is lazy too. Nature's looking to lower energy. We're always kind of working our way to sort of minimizing our energy. And we've been talking about intermolecular forces, that energy or those forces of attraction between our molecules. So we have interactions between the solvent and the solute, and the interactions between the solvent and the other solvent molecules, or the solute and the other solute molecules. So we're looking at sort of the relative size of those interactions. Do the solute and the solvent prefer to be together, or do they really like each other an awful lot, like themselves an awful lot, and prefer to stay with their own kind, in which case they're not going to mix. That's going to require a lot of energy. So we have that sense there from these energy considerations that like dissolves like. Okay? And by like, we mean like in intermolecular forces. They have similar intermolecular forces. So that's why this chapter had to come after chapter 11. We're looking at those forces there. All right. Questions on this? Good. I should check. I forgot to check if you were all alive and well out there. I guess I should check for a thumbs up, see how we're doing. All right. Good. I'm glad that the rest of us have made it here. Perfect. All righty. So I have a question for you then. Why don't grizzly bears dissolve in water? They certainly are fat. Certainly after they've been eating all these salmon up out the river. Sure. All right. Which is kind of right, because they are not polar bears. If they were polar, they would dissolve in our polar water molecules, wouldn't they? All right, maybe not. But they are fat, right? And fat is predominantly, it's a lot of carbon and hydrogen chains, which are not water soluble. They don't mix with water. They are not like water. So our fat little grizzly bears would not dissolve in water. All right. Okay. To be fair, it's a different kind of polar for the polar bears. So do not be alarmed. Our beautiful white polar bears will not be dissolving into the ocean anytime soon. All right. Okay. Enough silliness. Let's do science. How about that? Okay. All right. Let's take a look at them, since I promised we were going to look at things also energetically as well. forming a solution, right? So we've got our separate solute, those are our red molecules, and our solvent, which is our blue molecules, our little blue balls there. And we want to end up with a solution where they're all mixed and jumbled up over here. So we can see, right, there's a lot more disorder over here, and here they're pretty organized, right? Our molecules are reasonably organized over here. So we're going to think about this happening not in just one step, not just fruit, we're going to mix them together, but we're going to think about it happening in 3 separate steps, right? Sound familiar? Does this sound like something we did maybe with the Born-Haber cycle? So instead of thinking about an ionic compound forming, we thought about it in that long roundabout way with lots of separate steps. Here we're only going to go with 3 steps to form our solution. So again, these are imaginary steps. They don't actually happen in this order on our time scale, but it's helpful for us to think about the energetics in terms of these 3 separate steps. All right, and I think we did, again, a pretty good job of describing them in your preparation guide, 13.1, this one. So we're going to think about taking our solute, and our first step, we're going to expand it. We're going to separate those solute molecules from each other. So they are going to be, we're overcoming those intermolecular forces that the solute has. We're breaking those connections there, whatever those forces are that we're holding it together. We're going to expand it, and that's of course going to take energy. We'll think about our second step as well. If our solvent and our solute are going to mix, our solvent's kind of got to spread out a little bit and make some room, right? It's kind of got to tidy itself up and move things around and make some space for those solute molecules to get in there and mingle. And that's going to require overcoming the intermolecular forces that our solvent has for itself. So that's also going to require energy. And then lastly, we're going to take our all spread out solute and our all spread out solvent, and then we're going to let them come together and share space and mingle and mix. And they're going to form some intermolecular forces. There's going to be some attractions between them of some kind. Might be a lot, might be a little bit, but they will lower their energy by being together, and that will release energy. That'll be an exothermic step. All right, so step 1, break the solute-solute interactions, always endothermic. Step 2, also always endothermic. We're going to break the solvent-to-solvent interactions and attractions. And then step 3 is always going to be exothermic. We're going to form some new attractions, right? That's going to lower the energy and that will release energy, always exothermic. We call that the heat of mixing. Okay, so 3 steps. The heat to separate the solute, the heat to separate the solvent, and then the heat that we are receiving back when we allow the mixing to happen. All right. Yep, go ahead. Question, Raya?
Yes, Professor. So my question is, it needs to form before you can count it as the change of the solution.
Right, right. So it's the combination of all 3 of these steps that we call the heat of solution, right? So when we measure the heat of solution, which by the way, we have done, that was what we did in our lab. We measured the heat of solution when the sodium hydroxide dissolved.
Right.
All 3 of these steps happened. We didn't measure any of them separately. Again, we're imagining them happening separately. Mm-hmm. You can think about what forces might be important for one part versus another. Again, of course, they all happen at once.
Right, okay.
Yeah, yes, so thank you. Yes, the heat of solution is what we're trying to figure out. And that's the question down there in the box. So the heat of solution is the sum of all 3 of these steps. So if 2 of the steps are endothermic and 1 is exothermic, is the heat of the solution endothermic or exothermic? Right, we don't know, right? Because we have to know something about the size of these things. So to be fair, the answer is, in general, the heat of solution could be exothermic. I think it was for our lab. or it could be endothermic. It might require energy and actually cool things off, which is how a cold pack works. That's what's going on. It's a reaction, a dissolving reaction that's endothermic. So let's look at some energy diagrams for these 3 steps. We'll show how they're put together. The situation on the left is for when it's overall exothermic, and the situation on the right is for a heat of solution that's overall endothermic. All right, so let's focus on one at a time so we don't get distracted. We'll look over here on the left with the exothermic version. Okay, and here's our 3 steps. Here our solute is orange instead of red. All right, so our solute, we start out at some energy level, and we have to go up in energy. It takes energy to separate our solute. So that's step 1. It absorbs some energy to go up here. Step 2 is to separate our solvent. That also requires energy. So we go up in energy again. Right? So it kind of looks like a Hess's law kind of cycle or energy level diagrams we've been drawing for a while. Okay. So way up here, we have these separated particles. We've got our solute that's all separated and our solvent that's all separated. And then step 3 was the mixing, allowing them to come together and interact, and they'll form some attractions with each other, and that will lower their energy. So that's exothermic. And here it's very exothermic, and it's more exothermic than these are endothermic. So we're looking at the relative size here. So when our heat of mixing was way more exothermic than our separating our solute and separating our solvent were endothermic. Right? So when the size of that is bigger, we end up with an overall, right, going from here to here is the heat of solution, taking our solute and solvent that are separate and turning them into a solution. Okay? So in this case, it was exothermic. Right? We had a bigger heat of mixing than we did our sum of our heat of solute and solvent. All right. On the endothermic side, we have exactly the opposite situation. So again, we have our solute and our solvent. Again, to separate them, it's always endothermic. It took some energy to separate our solute. Then it took some more energy to separate our solvent. And we end up here with our separated particles all up in the air, all ready to be mixed together. And we allow them to come together, and they'll form an attraction, and it'll be an exothermic process. Here, it's just not a very exothermic mixing process. So we only come down in energy a little bit. And overall, right, from our starting point to our forming the solution, our heat of solution this time is positive. We have to go up in energy. We have an endothermic heat of solution. Both are possible, right? So it just depends on the relative size. And of course, we have to deal with entropy as well. There is on Blackboard a nice video that kind of goes through the energetics again in some detail like this. So if you want to kind of hear that again, there's a link to a video on a Blackboard in the beginning sections of chapter 13. But here's the summary from that. So I want to kind of look at this so we can see why like dissolves like, okay? Why polar solutes and polar solvents end up giving us a situation where a solution will form, right? So let's kind of keep in mind these diagrams here, what the relative sizes are representing, right? What is costing us energy? Separating things cost us energy, our solute and our solvent, and what is gaining energy when we let them mix together and form that solution. So let's look at our combinations. We'll start right at the top there. If I have a polar solute and a polar solvent, they're held together with those dipole-dipole intermolecular forces. So that's a reasonably strong force, right? You've got a positive end and a negative end of your molecule permanently, right? So there's going to be some attraction there. So our heat 1, which was to separate the solute, is going to be reasonably large. And our heat 2 to separate the solvent, also polar, will also be pretty large. And then when we let our solute and solvent come together, that's delta H3. They're both polar. Oh, they're having a great time together. So there's, again, a large release of energy. It'll be negative. That's the release part. So overall, our delta H for our solution, right? We've spent a lot of energy taking things apart, but we've gained a lot of energy back when they recombined. So overall, the delta H for our solution is probably a reasonably small value. Might be a little bit positive, might be a little bit negative. But either way, a solution will form. Right? If it's a negative exothermic, remember exothermic is very favorable. Nature favors that because we're coming down in energy. But even if it's endothermic, if it's not hugely endothermic, entropy then can take over. Entropy can say, hey, I know that's going to cost a little bit of energy, but we're going to make a great big mess with it. Let's do it. And a solution will form. Right? So so it doesn't matter if it's slightly positive or slightly negative, a solution will still form. Entropy then becomes our sort of our driving force to kind of push it over the edge into forming a solution. Okay? If we drop down to where our solute and our solvent are both nonpolar, these are things that don't have a dipole. They're not forming hydrogen bonds. They only have those London dispersion forces, which, as we know, are pretty weak kinds of forces. So the energy that it takes to separate the solute from the other solute molecules is, again, a pretty small amount of energy. Our energy to separate our solvent, also just held together with dispersion forces, pretty small. And then the energy we get when we put them together, they're both not polar. So again, they're both still interacting in terms of London dispersion forces. We'll get a little bit of energy back. Again, they're all kind of on the same size scale here. So whether we go up in energy and then down in energy, it kind of almost balances out. And again, our delta H for the whole solution process for all three steps put together is pretty small. So again, whether it's a little bit positive or a little bit negative, entropy will help us out here and a solution will form. Those two situations that are in the darker blue are the like situations. Like dissolves like. When they're both polar or both nonpolar, we end up energetically with a situation where a solution will form. The other two are where there's a mismatch. So let's look at one of them. If we've got a nonpolar solute and a polar solvent. So our solute is not held together really well from the molecules to each other. So that's going to take just a little bit of energy to separate them. But our solvent is polar. It's going to take a lot of energy to separate our solvent molecules to make room here. So that's pretty expensive in terms of energy. And when we bring them together, we're going to bring together something that's polar and something that's not polar. So they can't interact with a dipole force because only one of them has a dipole. So it's going to, when they interact, it's going to be kind of on the terms of the worst sort of force. So really all they've got is dispersion forces to interact with each other. And that's a small amount of energy, relatively speaking. So we've spent a lot of energy and we're getting back only a little bit. So our overall delta H is going to be a large, relatively large and positive value, endothermic. That is not favorable. And that's asking a lot for entropy. Entropy can't overcome a very large value of endothermic reaction. So no solution will form. It's not favorable. It doesn't happen. Those two things would not make a solution. And the same thing happens in the reverse case, when we have a polar solute and a non-polar solvent. It just costs too much energy to separate everything for the amount of energy we're going to get back when we bring them together. So that is the long and energetic story behind like dissolves like. Okay. Questions out there? No? Okay. All right. So let's take then another look at a slide from back in the day. All right. So we had this slide back in chapter 4. When we first started talking about solutions and how they form, we had a couple of different kinds of compounds, either ionic ones or molecular. We call them covalent as well, where they're sharing electrons. So we had those two different kinds of materials, and we looked at how they interacted with water in particular. And again, these are the same slides. All I've done is I've added some color to them. I've added some red and blue to kind of point out how we have talked about these things before, although we didn't call it this. So in the ionic one, let's start on that side. We said that the individual ions get surrounded by the water molecules, right? So when ionic compounds dissolve, they break apart into their ions that make them up. That's what we had done before. Well, what are we doing there? When individual ions are surrounded by water molecules, that's basically the water molecules separating and surrounding or mixing with the ions, right? So those are the last two steps, steps 2 and 3, that we just talked about. Separating the ions, taking that last, that is the energy of our solute, right? Separating our solute into its individual pieces. So again, we've kind of talked about this before, but we just didn't use these words at the time. When we have our molecular compounds, so these are things that don't form ions, we again talked about individual molecules being surrounded by water molecules instead of forming ions. Again, that's still those same two steps. The solvent has to separate, the water has to make room, and then we have to mix our molecules of interest with our water molecules, and we'll gain some energy back depending on how they interact. We also have to separate our solid into molecules. So not into ions, but into the individual molecules that make it up. We're breaking those intermolecular forces that hold one molecule to the next one to make a solid, typically. So that is delta H of our solute. Okay, so here we are just putting some of our new words into our old structures, our old bits of information that are already in our brain there. So hopefully that will help us. But this is a special case. So this is the special case of dissolving in water. And we do have some special terms, some special ways of thinking about it, specifically for our ionic compounds. So what we're going to do is we're going to look at another energy diagram, again, both for exothermic and endothermic, for an ionic compound. And here we're going to combine a couple of terms. We're going to combine these blue terms here into one. Right? So instead of thinking about them as two separate events, we'll think about them as one event for an ionic compound, and we'll see why we do that. All right. So again, special case. Right, so not for everything, just for the ionic compounds in water, So we're going to put together the energy it takes to separate the solvent, water, and the energy we're going to get when we mix our ions with our water. And we call that the heat of hydration. So we're hydrating, or we're putting water around our ions. So that's where it gets that special name. So that's why there's only 2 steps on these little charts here. We go up and we come down. We don't have the 2 steps up and 1 step down like we had for the more general version. Okay. So the reason we do this is for an ionic solid, the energy it takes to separate the solute, that very first step, is the lattice energy. Oh, there's a blast from the past, right? I know we love lattice energy, don't we? We all wish we could draw Born-Haber cycles all day long, don't we? Yes. You can say yes. You can lie to me. It's okay. All right. All right. So lattice energy is that we thought of it in the reverse direction. We thought of it in terms of how much energy is reversed. How much energy do I get back when those ions form the solid? So here, we're taking apart our solid. We're doing the opposite. We're doing the opposite or the negative of lattice energy. So that first step, that endothermic step, is going to be the lattice energy. So we have some ideas, or we can compare different materials in terms of their lattice energy based on their charges and their sizes. We had those trends that we can think about. But lattice energy, here's another way to think about lattice energy. Okay, so we'll separate our ions, fly them up into the air and make them gaseous. And then we'll let them get hydrated. Right? We'll let the water molecules separate and mix with them. That's the heat of hydration. So it combines the solvent and the mixing process. And we end up then with our dissolved ions. We end up with our solution at that point. Right? So in this case, our heat of hydration was bigger in size than our lattice energy, right? In size, in amount of energy. So we ended up with an overall exothermic process for dissolving. Okay. Over here on the endothermic side, we have the opposite case. So on the endothermic side, our lattice energy is bigger in size than our heat of hydration. Okay. That's how much energy we get back when we let them mix. So overall, in this case, our delta H for our solution is endothermic. Right? So we didn't get back as much as we had to spend to pull these ions apart out of the lattice. All right. So again, it can be either, and whether it's exothermic or endothermic for the solution forming, it all depends on the relative size of these two things: lattice energy, which we've talked about before, and heat of hydration, which is our new thing that relates to intermolecular forces between the ions and the water. Oh my goodness, all sorts of things coming together. And how about these? We talked about whether things would be soluble, make a solution, or not soluble, not make a solution for ionic compounds in water. This is what we're talking about, ionic compounds in water. These rules are just general summaries based on observation, right? And they are related to the lattice energy of these things. So these things that tend to be insoluble are going to be those things with relatively large lattice energies that don't let us gain as much energy back as we spent trying to take these lattices apart. So we end up with very endothermic kinds of heats of solution, and they're not favored, right? Entropy can only do so much, so they end up being not soluble, no solution forms. Right? Versus these things that are soluble, that we thought did make a solution, these are ones where the heat of hydration is enough. It overcomes all of those sort of bad things that can happen when we're trying to take our lattice apart. So all that energy we spend taking them apart, we more than get back when we reform that mixed solution. So these solubility rules that we've had and we've been kind of playing with off and on really are related to the energies and these lattice energies that we learned about in the last few chapters. So it all kind of works together, and it's a beautiful thing. All right. Anybody get goosebumps from that? I thought that was cool. Nobody? Just me. Okay. Oh, tough crowd today. Okay. All right. Other questions on forming solutions? So
Could you
go ahead.
go to the one with the cycle? I think it was this one. So I'm confused on where you're starting, because why is it on the exothermic side that the change in the solution is going down? Does that mean that it's taking, it's releasing energy in order to
Right. So after it's mixed, it ends up being lower in energy than our starting out. Our starting out position is the separate solid, the separate ionic compound, and the separate solvent. So we will first separate our solute, and then we're going to gain some energy back when we let the solvent and the solute mix together here.
oh, my question arrow, not the hydration.
Mhm. So your question is again, let me make sure I understand.
It's the red arrow that says the change in heat of solution.
Uh-huh.
Why are you starting on the second one for the solid, but on the for endothermic it starts on the first?
Oh, because it just starts out higher in energy, right? I didn't draw this on the same scale. I didn't put it at the same position because then everything would have just been higher up. So I just shifted everything down here. So again, there's no energy, there's no scale here. So there's no sense of absolute where this is. Just a sense of, yeah, we always start with our separate solid and solvent. Whether that energy position is at the bottom or in the middle, it was more so you could see that this one ended up higher up.
Okay, so the energy for the exothermic one, it used less than it would for an endothermic to go from a solid to the gaseous ions.
Right. It didn't take as much to go up as we got back. Right? So however much energy it took us to go up to the top, we got back more than that. We came back all the way down and then some. Versus the endothermic, we spent all this energy to get up here, and when we turned around, we only got a little bit of it back. So that's why we ended up at the end of the day at a higher position in energy than we do over here. Here we end up below where we start.
Right. What is the significance of the change in solution? Because that's the only thing that's really throwing me off.
Right. So that's just the sense of when we dissolve something, is it going to release energy or is it going to absorb energy? Right? Releasing energy is favorable. That encourages a reaction, a solution formation to happen. Endothermic is not favorable in terms of heat. So that requires enough entropy, enough disorder to be forming to overcome that for a solution to form.
Okay, so the endothermic is
it's generally not favorable, especially if this energy is too endothermic, if this is a very big value. And that's what our solubility rules tell us. It gives us that general sense of, well, what's winning here? It gives us that sense of, in general, is a solution going to form? Is entropy going to be enough to overcome any endothermic things? Or is it just going to be exothermic and be favorable all the way around? Yeah. So like I said, we've been kind of playing with this idea without really knowing why these rules were the way they are. Right now we've got a little bit of a background to it.
Okay, thank you.
Okay, good. All right, other questions? Oh, go ahead, Alex.
Oops, sorry. So I guess I'm struggling a little with looking at the equation at the top and then understanding how that relates to the image.
So this one here?
Yeah.
Okay, so the equation at the top is telling us what the heat of hydration is. So it is two of the three steps that we had talked about. Oh my goodness, way back here. So the heat of hydration is really the combination of the solvent step and the mixing step. So it's just it's kind of skipping, writing them as two separate steps. It thinks of them as one thing. Since we're always talking about water in this case, it's just kind of blended in or kind of part of that third step, the heat of mixing. So that's why I said this was for a very specific case of ionic compounds in water. Right? We can't have a lattice energy if we don't have an ionic compound. And if we don't have water, we don't have hydration. We just have solution forming or mixing going on. So this was just our very specific case here. Okay. Are there follow-up questions?
So, to just review
Mhm.
the order of events, I guess.
Yes, okay.
It's going from the left side, starting at the solid,
Starting at the
Or-
solid.
and then it goes up from there and around.
It goes up and around, right? So we're
And
gonna,
that amount is equal to the change in heat for the solution.
the heat of the solution, right? So again, we're just thinking about this heat of solution in an imaginary set of steps, right? Again, it doesn't really happen this way, right? When you dissolve your salt in water, it doesn't all go up into the gas phase and then wait for the water to open up and then mix together, right? It just happens, right? It all happens at once. So this is, again, our way of kind of trying to visualize the multiple things that need to go on, the kinds of energy that needs to be spent and gained. So yeah, so we'll take our solid, we'll think about separating it, and then the heat of hydration is the combination of the water making room and the water surrounding our ions. So it's the same 3 steps. We've just plopped 2 of them into one situation, into one process. Okay. Well, how about we let that settle for a little bit, and let's take 5 minutes, stretch our legs, and then we'll look at some factors that affect solubility and see where we get before we stop to work on our problem set. All right, so let's come back at 7:20, and we'll look at some things that affect solubility, how to make it more or less soluble. All right. So hopefully we've stretched our legs and maybe gotten a little snack there or something. So now it is time to think about how we can, now that we've got our solutions either made or not made, let's see if there's a way for us to adjust that solubility. We'll see what solubility is and then how we can control it. All right. So we'll start just by sort of imagining some things that we are familiar with. All right. So what happens when you put sugar in your coffee or your tea, if that is your thing? What happens when you put a spoon of sugar into it?
It dissolves.
It dissolves, right? And it's delicious and it's lovely, isn't it? So what happens then when you put 2 scoops of sugar in your coffee? Yeah, it does. It still dissolves. It gets even sweeter, right? It's even more delicious. All right, so let's go crazy. Let's try and put 4 scoops of sugar in our coffee. Now what happens?
It reaches a point where there's more sugar than coffee.
Yeah, right. At some point, it just stops dissolving, right? There is, right? We know there's a limit, right? We know you can't keep putting sugar in your coffee and have it get sweeter. And like, there's a limit, right? So we cannot put a certain amount of, we can't just put an infinite amount of sugar in our coffee, right? Someone needs to tell Mr. Wollman this. I don't think he's aware of this. He regularly violates this rule. So this limit to how much of something can dissolve in a solvent has a name, right? And it happens to everything, and it is called our solubility. So here are some things that we're going to think about, factors that are going to affect it. What is that equilibrium? What is that natural position? What is that natural amount of material that can dissolve in another material, into a solvent? And then how does pressure and temperature come into play for our different materials that we're trying to dissolve. So we can try and control that solubility and affect it or adjust it to meet our needs. All right, so here we are with equilibrium. So that's, we had this sense before when we talked about vapor pressure, and we talked about that dynamic equilibrium, that kind of back and forth, where some of our liquid was going to the gas at the same time some of our gas was becoming a liquid. There was that balance where it looked like nothing was happening, but in fact, there was lots of things happening. It's just that there was no net change. And that's what's going on when we have that middle situation. So the middle situation is called our saturated solution. It's when we have as much stuff dissolved as we possibly can. So that's our limit. That's the natural limit. And at that point, our solution is going to have the most amount of solute that it can have in it. And our solute will be in dynamic equilibrium. It'll be dissolving and undissolving, right? Or crystallizing is our fancy word for that. But it'll be going back and forth, right? But there'll be no net change. No more stuff will get into our solution. If you think about it, the concentration, the molarity, if you will, or any of our other concentration units stays constant. It's the maximum that will dissolve at that temperature. Right? If we have an unsaturated solution, that means we're not yet at that limit. So this is our cup of coffee with only 1 scoop of sugar in it. We're not yet at the limit. We can still add more and it will dissolve. Right? So that's the situation where we have an unsaturated solution. And under certain situations, certain circumstances, we can force our solution to be what we call super saturated. So over full, right? This is kind of like, again, if you've eaten too much, right? It's uncomfortable and it's unstable. And if someone jostles you, stuff's going to happen, right? Things are going to come out. That's what happens with our super saturated solution, right? It's very unstable and it's very easily disturbed. So if you put in a seed crystal, so a little bit of the solid in there, eventually the solution will figure out, oh my gosh, I shouldn't be this full. And things will come out of solution very quickly. And I think there's some nifty little videos on Blackboard for that as well. So you can kind of watch things recrystallize very quickly because they were over full. So that's kind of a neat thing to watch there. All right, so our first situation, the unsaturated, where there's more that could dissolve, that means we're not yet to that limit. We're not yet at that equilibrium. So more things will dissolve than things are recrystallizing. In the middle, we are at equilibrium. Right? So that means that what's dissolving is happening at the same rate of things recrystallizing. So there's no change, right? That's the maximum amount of stuff we can dissolve in there. And then we have our unstable, overfull, supersaturated solution over there on the very, very far right. Okay, so we'll just get some definitions down there. So we have some words there. And now we want to talk about, well, how can we affect this, this solubility equilibrium? How can we maybe shift it a little bit so that either more or less things will dissolve? So here's where temperature comes into play. So we're going to talk about solids and gases separately because they're going to behave a little bit differently. So we're talking about the solute now. So when the solute, the thing that we are dissolving, is a solid. For most solids, not all, most. When we increase the temperature, we are going to be increasing our solubility, right? We've added more energy, right? Kind of makes sense. We're going to be able to pull that solid apart. We've got more energy to do it. We've got more energy to separate our solvent. Everybody's got more energy. There's just a little more room all the way around. So in general, most solids behave this way. There are a few, right? There's a nice graph in our textbook that shows how solubility, the maximum amount that will dissolve, how that solubility changes with temperature. And for almost every solid, it increases as temperature goes up. But there's one or two where it goes the other way, where it decreases as the temperature goes up. So again, in general, though, most solids. So if Mr. Wollman would heat up his coffee a little bit more, he could put more sugar in his coffee. Still not 4 scoops, but he'd get more in there. That's what we will say. For gases, though, the opposite happens. Let's think about why that is. So when we increase the temperature, we have less solubility. So again, thinking about our gases, we've somehow managed to get them into a liquid and confine them. But now we've given them more energy, right? So our gases are now more able to escape. They're available to them, so they can leave, right? They're going to use that energy to leave and make bubbles and go out of our drinks, right? So that's why soda goes flatter faster in the summer than it does in the winter. Right? It's a solubility effect. When we have more temperature, more of our gases are going to leave. They're going to be less soluble. They're going to be not as many in our liquid, which is just another problem with heating up our global temperatures. As our oceans get warmer, less oxygen can be dissolved in them, which is less oxygen available for all the little fishies and things that live and rely upon that. So that's another concern there. All right, so for temperature, for gases, more temperature, less solubility. For solids, almost all of them, but not all, but most, when the temperature increases, they become more soluble. So again, we have to know something about what is our solute? What are we trying to do with it? All right, questions on that? Have you all run off to the microwave to heat up your tea to see if you can get more sugar in there? Maybe a little bit, okay. All right, so pressure is not really going to be a factor for our solids. They're really they're not sensitive to pressure, right? Their molecules are already pretty close together in the solid form. So a little more pressure isn't really going to do anything for them. But gases are going to be sensitive to pressure. So if we're trying to dissolve a gas into our liquid, if we increase the pressure, right? So basically apply more pressure of that gas above that solution, right? So it has to be that gas. So you can think of it as the partial pressure of that gas above the solution means if we increase that pressure, we'll be able to effectively kind of force or press more of that gas back into the liquid and be in the solution. So we would increase the solubility of our gas by increasing the pressure of that gas right above that solution there, which is kind of how we get carbon dioxide into our soda pop. We have it under pressure. We sort of forced or pushed that in there. So when you open your soda, the twist top or the pop top, and you hear that psh sound, that is the pressure being released, right? That's the sound of the pressure that was forcing all of that carbon dioxide bubbles to stay into your solution. All right. See, we've learned something today, something useful. All right, and there is a relationship that tells us how that pressure and that solubility, how much stuff is dissolved, is related to that pressure. So there's a constant, it's called Henry's law, and not mysteriously, the constant is called the Henry's law constant. So it's the constant that relates pressure and solubility. So typically, our solubility is in concentration units, typically moles per liter, typically molarity. Our pressure of the gas is often in atmospheres. And then our Henry's law constant will be in units that tell us that. The Henry's law constant then would be in units of molarity per atmosphere. It's kind of a bizarre unit, but it's the one that makes this relationship work here. Okay. I don't think we won't do one of these. You have a question in your problem set on that. There's not a lot of moving parts here. So it's really a matter of making sure the units of your solubility, concentration units, and your units of pressure match whatever you have for your Henry's law constant. So as long as those are all compatible, we have this pretty simple little algebra expression for how those are related. Okay. So let's do a couple of quick, let's test our knowledge here. We'll see how much we've retained here. All right, so which of these are solutions? Homogeneous mixtures. Which of these are solutions? Might be more than one answer. All right, so if you've got your camera and your cards, you can do that, or we can use the chat box to put your answers in there. All right, which are solutions? I'll tell you there's more than one. Would you be surprised? Yeah, some folks have said all of them, right? So again, it kind of depends on where you put your eyeballs. But yes, there are 3 that are considered homogeneous mixtures. All of them are uniform in appearance. I hope your breath is uniform in appearance. I hope there's not chunks of things coming out when you breathe, unless you had garlic for lunch. So a homogeneous mixture or a solution does not have to be a liquid, even though we have talked almost exclusively about liquids today, specifically water solutions. But your breath can also be a solution, and sweat and tears are definitely water-based solutions. They're full of mostly salts and a few oils and other things. Blood, again, depending on where you put your eyes, can look like a uniform mixture all throughout. But again, it's really kind of in that in-between ground, in that colloid zone in the middle where it's not really, where it scatters light. The things or the particles that are in blood, that are dissolved in blood, red blood cells, white blood cells, are kind of on the bigger side. So that's why sometimes we don't consider blood to be a solution. Alrighty, so it's a reminder of some old terms. All right, here is a challenging one. All right, so we'll have to get our brains in high gear. So rank these compounds according to their increasing solubility in water. So you want to start with the one that is the least soluble, that does not want to be in water, and work our way up to the thing that wants to dissolve in water the most soluble. All right. So what are you going to think about? What features are you looking for in and among these molecules? What are you comparing them based on? All right, yes, always a good answer. Intermolecular forces, always a good answer, right? We talked about how like dissolves like, okay? So if we want to dissolve things in water, we're going to look for the things that are the most like water. Who can do things that water can do in terms of intermolecular forces? And which things are not like water, right? Which things do not want to be in water, are not able to do any of the fun things that water can do, like hydrogen bond or be polar. Okay, so we want to put them in order from lowest solubility, the least like water, to the most solubility, the ones that are the most like water. Okay, so we've got a few votes coming in now that we've had a chance to think about it. All right, so we've got a lot of A's and B's. Let's again. All right, lots of A's and B's. All right, so So here's the answer. The answer is in fact D. All right, so let's see why that is. So I think we've correctly identified that our first compound here is made of only carbons and hydrogens, only has London dispersion forces, which is very much not like water. So it's going to be the least soluble. It's going to be the least likely to dissolve in water. So compound 1 is definitely our least soluble. So how about the most soluble? Let's kind of look at the other end of things. Which of these compounds is the most like water? Which of them can form hydrogen bonds? Which of them is polar? So we had some choices of A's and B's were our choices. So some folks were picking compound 2 or compound 3 as being most like water. What do we think? Which one is most like water?
Professor, for the last one, those both can exhibit hydrogen bonding, correct?
They can, right? So 3 and 4 can both do hydrogen bonding, which is just like water. So that's why those two are above number 2. Number 2 is polar, but it can't form hydrogen bonds. So that's why it's below 3 and 4. Why is 4 more like water than number 3? Okay, so let's take a look at that. And they can both form a hydrogen bond, so that's great. They're both pretty happy to be with water. But number 3 has a couple of carbons hanging off of it, so it has kind of almost like a little tail on it. That's not polar. That whole end of the molecule really isn't polar at all. Versus number 4, who only has one little carbon on there, so it's kind of just got a little round end instead of a great big tail there. In terms of the not polar part. It's small. The last one is small like water, so it can kind of fit in and get close to water. So although both 3 and 4 can both do hydrogen bonding, the one that's the most like water in size and in not having a whole bunch of not polar parts to it would be number 4. So that's why number 4 was at the top of the list instead of number 3.
Professor, when you say size, you're not talking about molar mass. You're talking about like the construction of it, the structure.
Well, it's a little bit of both for this one. So for number 4, it only has one carbon kind of hanging off the backside, and this number 3 molecule has 2 carbons in a chain hanging off its backside. So it's got a bigger mass or a bigger area, a bigger section of that molecule that is not polar, that is going to kind of be fighting the polar nature of water. So it's going to be kind of almost negating some of the hydrogen bond effects.
Okay, and number 2, it
Number
doesn't
2,
have hydrogen bonds because oxygen is by itself.
because oxygen is by itself, right? So there's no hydrogen bonding in that middle molecule there.
Okay, thank you.
It is polar though. So it will probably dissolve in water. It's just not going to be as dissolving or as soluble. It'll have a smaller amount that can dissolve than these other 2 down at the ends there. All right, so that was a pretty high level question. Let's try a fill in the blank question. All right, so entropy. Let's fill in the blanks. Tell me something about entropy. And again, remember, there can be more than one answer. All right, what do we remember about entropy? All right, so remember that entropy is that tendency or that drive in nature to be messy, to be disordered. Okay. So we'll let a couple more votes come in. We'll see how we do. Okay, It is, in fact, A and C. So because entropy is that drive or that desire to be messy, that is exactly what a solution forming is. It's a messy thing. There's lots of ways for those things to be mixed up. So it drives that solution formation, and it can overcome, right? That sense of messiness can overcome what we called unfavorable energetics, an endothermic heat of solution. That was unfavorable. So it can overcome that. It can say, you know what, I know it's going to cost energy, but we're going to make a mess and it'll be great. So we can overcome those unfavorable energetics, that endothermic heat of solution, and actually a solution then will quite naturally form. Right? It is not proportional to the heat of solution. It is an unrelated, different process. It's related to disorder, and the heat of solution is related to enthalpy. So that's why B is not our answer here. All right. Questions on that? Okay, we've got a numerical one to play with here in a little bit. So first we'll do one more kind of a true false kind of thing. And then we'll do a calculation here, a very simple one. So which of these statements is or are true? So there can be more than one. So the solubility of a gas in a liquid is always increases with increasing temperature. The solubility of a solid in a liquid always increases with increasing temperature. And then according to Henry's law, right, so you got to remember what that is. That was the one that related solubility and pressure. So according to Henry's law, the amount of gas dissolved in a solution is directly proportional to the pressure of gas above the liquid. All right, so we're looking for the true statement here. Yeah. Okay. All right. All right, it is C. It is C. So a lot of folks also picked B, but I will remind you again that the solubility of a solid in a liquid usually increases, but not always, right? So most solids will increase with increasing temperature, but not all of them. So it's not an always situation. It's a usually or a most always situation. But I'm glad nobody picked A. Everybody got that the solubility for a gas was inversely related to temperature. So good, good, good. And then Henry's law, directly proportional means they increase together. So when pressure goes up, the solubility goes up. So that is our directly proportional. So we had to remember what that word meant. We've used that quite a bit with a lot of our relationships throughout the semester. All right, go ahead, Amanda.
Hi, Professor. I was wondering, I didn't see a specific example in our book. Can you give an example of a solid in a liquid where the temperature is increasing, but the solubility is not increasing?
It is, oh gosh, I'm not gonna be able to think of it off the top of my head. I want to say there's a graph in our textbook, which is escaping me right now. But it goes the other direction. I'm gonna blank on it right now. I'll have to look that up. But yeah, there's just, it's like very few, almost all though.
Okay, thanks.
Well, I will have to look that one up. Yeah, I don't know what it is off the top of my head. I didn't think to write it down. But yeah, so I will look that up. I will look it up at a rate because it's going to bother me until then. So solubility. All right. Thank you. Okay, good. All right. let's try a numerical problem related to those energy level diagrams. So it may be helpful to sketch it out. So as you're thinking through this problem, try and sketch out what's going up and what's going down in energy and what are the relative amounts here. So let's look at this specific example. So here we know that the lattice energy of sodium iodide, NaI, is negative 686 kilojoules per mole. Remember, we defined it in terms of how much energy is released when those ions come together to form the solid. Okay, and the heat of solution, so the overall result of going from solid to dissolved solid is negative 7.6 kilojoules per mole. And your job then is to calculate the heat of hydration for sodium iodide in kilojoules per mole. All right, so it may be helpful to sketch out an energy diagram and kind of label the amounts of energy and get them in proportion for an exothermic or endothermic reaction, whichever you have decided it is. All right, take a little bit to work on that.
Professor, do we need to make the lattice energy positive?
Right. Well, remember whenever we are doing these cycles, we often sort of just think about the size of the energy. So yes, right, because we're doing the opposite of lattice energy when we're making a solution, right? We're taking the lattice apart. So we're spending energy, right? So for us, we're going to start with that solute, the NaI, and we have to add energy to separate it, right? So we're doing the reverse of lattice energy. So it'll be a positive value, yes. Okay. So I'm going to put up an energy diagram so we can kind of visualize sort of the direction and the size of energies there. All right. So it is negative 694 kilojoules per mole. Now remember, the heat of hydration is always going to be negative. We're always going to be getting energy back. The question is whether we're getting a lot of energy back relative to how much we spent for taking things apart, or whether we're getting less back. So here's what the diagram looks like, right? So we know that the heat of solution is negative 7.6 kilojoules per mole. So we know that the heat of solution is lower in energy, where we're going to end up lower in energy than we started. That's the overall process. And then our two steps are going to be the opposite of lattice energy, right? We're going to be taking things apart. So we're going to spend energy. We're going to spend 686 kilojoules. And we need to look at, well, how much energy am I going to get back? Am I going to get back less than that or more than that? And the answer is, just from looking at the diagram, I'm going to end up with more energy coming back to me. Right? I was here at this level. I went up 686, and then I came down and I ended further down, lower than I was before. So I have to have a bigger heat of hydration than I did of my lattice energy. Right? And because I'm coming down, it's going to be a negative value. So that's why it's 7.6 kilojoules bigger in size and with a negative value. Okay, so we can see that the size of these two arrows, the heat of solution and the lattice energy arrow, the size of them has to equal the size of our heat of hydration. Right? So the same kind of thinking we did with that wild Born-Haber cycle with the 10 million different arrows, we can do that for something that only has 2 or 3 arrows on it. All right. So you get to practice another one of these on your problem set as well. Question, go ahead, Raya.
Professor, so you're adding negative 7.6 and then you're adding the negative 86.6 to give you the heat of hydration.
Right. So again, focus on the size, not the minus and the plus. The minus and the plus just says whether it's going up or down. We know that the distance from the bottom to the top has to be the same, whether we go through these arrows or this one arrow. They have to be the same size because they start and end at the same place. So just looking at the size, the number, the amount, the lattice energy amount is 686 kilojoules, and the heat of solution amount is 7.6 kilojoules. They're adding together, right? Those two arrows, that distance is going in the same direction. So this amount of energy, 7.6 kilojoules, and this amount of energy, 686 kilojoules, has to equal this amount of energy, 694 kilojoules. No, it's negative because we know we're coming down in energy. So we just kind of put that minus sign back on again.
Okay, and this particular one is exhibiting endothermic?
This one, well, for heat of solution, is it endothermic or exothermic? We're ending up lower in energy. We're coming down. Energy is being released. It's got a negative sign there. So this is an exothermic process overall.
Okay.
See how we get to review all of our stuff all at once? Look at that, all that chapter 6 stuff and a little bit of chapter 9 for cycling, all has come back into play here. Pretty nifty. All right. Other questions on this? All right. So put a note to yourself. There is a little question. One of the questions in number 2 in your problem set deals with something kind of like this, where you've got, it talks about this little tiny cycle here. So that'll be something you can put a note to practice with when we get to our problem set in a little bit. Okay. Oh, okay. Other questions? Alex, go ahead.
So if you were solving for the delta H for the solution, how would you know which direction it was going if you're just going with the magnitude?
Right. So if we had information on the size of the lattice energy and the size of the heat of hydration, that would tell you what's going on, right? Because we're always spending energy to break up the lattice. That's always a positive energy. So if our lattice energy was, say, 500 kilojoules, and we knew our heat of hydration was only 400 kilojoules, that would mean we're not coming down all the way, right? We're going to go up 500 kilojoules, but our heat of hydration is only going to bring us down 400. We're going to end up, the net process is going up 100 kilojoules. So my heat of solution would be a positive value at that point. So you've got kind of have to almost, really, at least mentally, sketch it out. Kind of sketch out the size of things so you get that sense of, am I spending energy and how much am I getting back? So that's what we're looking at, that balance between the two. That way we don't have to keep track of the minus and plus signs. We can just think about, did I go up in energy? And then how far down did I come? Did I come down more than what I went up? That'll be exothermic. Did I come down less than when I went up? And then it would be endothermic overall, the heat of solution. All right. We have to get, I think, a little more comfortable drawing these little cycles without having flashbacks to the Born-Haber cycle, I think. think we'll have to work on that. Okay. Good. All right. Well, let's dip our toes into tomorrow's topic, which is colligative properties. All right. These are they're a little weird to think about because these are the properties of our mixtures. Right? So these are things where the behavior of our solvent, which is our major component, is going to be changed or adjusted slightly depending on the solute, not even depending on the solute, depending on the concentration of the solute. The solute's identity doesn't matter, which seems like it should, but it doesn't. So that's what makes these properties a little odd and unusual, is that we're not going to be concerned with what those particular solutes are. We're only going to be concerned with what their concentration is. And the concentration units that are going to for us are going to be different for our different colligative properties. That's why we had to go through and learn about so many of our different possible concentration units that we did last week. All right. And we have, again, oddly enough, already studied a colligative property. Can you think of one? Can you think of something that we've worked with quite a bit, actually, that doesn't depend on the identity or the nature of the material that we are looking at? That only depends on the number of particles. Temperature is a good one. It doesn't depend on the material, but that one doesn't depend on the number of particles. We can have temperature of a small sample or a big sample. So it's close. It's close. Can you think of something we studied where we didn't care what the material was? We were just concerned with how many moles there were? Oh, how quickly we've forgotten. Oh, we've forgotten all about gases and pressure. And remember the pressure of a gas, it doesn't matter what the gas is. It just depends on how many moles of gas we have. So yeah, we've been working with this all the way along. Total energy does depend on how much stuff we have and what it is, because some things can hold more energy depending on their state of matter. So it's not energy is not quite the right thing. Molarity is one of our concentration units. So again, that will depend on what the solute is, because we always say moles of something, moles of a particular thing per liter of solution. But pressure is one that we've worked with before. The four colligative properties that we're going to work with are vapor pressure lowering, boiling point increasing, freezing point decreasing, and osmotic pressure, which will probably be a good and interesting one for anyone going into the health field. We'll have a nice example of that for us tomorrow. But let's remind ourselves about vapor pressure. It's a good thing because, hey, guess what? Vapor pressure is one of those topics we worked with already. That'll be in our exam tomorrow. So there's a good thing to talk about right now. So we talked about vapor pressure. So over on the left is our pure solvent. So remember when we put it in a container and slap a lid on it, it's going to create some vapor, right? So above that liquid, some of our solvent molecules are going to escape into the gas phase and create a vapor pressure, right? And we'll have more vapor pressure if we have lower intermolecular forces. More of our gas is going to be able to get up into the gas phase and leave the confines of the liquid there, which is great. So we talked about that before, and that all depended on intermolecular forces and what the temperature was. So let's come over here on this side, and we'll dissolve some of our green solute molecules. As you can tell, it's green now. Our solution is now got some solute in it. And the vapor pressure that's due to our solvent is now lower. So we need to explain that. We have a couple of different ways we can explain it, and they both kind of work together to explain it fully. So we can think of this, remember that there's a vapor pressure because our solvent molecules can leave the liquid and go into the gas phase, right? So our solvent molecules have to get to the top, right? They have to get to the surface and then leave, right? They've got to have enough energy to overcome their attractions. So let's imagine now there's a bunch of solute molecules hanging around, right? And basically they're standing in the doorway. They are blocking the way. They are keeping everyone else from getting out. So that's one way to think about how the presence of a solute will inhibit or slow down or decrease the vapor pressure. So our liquid molecules can't leave and become vapor molecules. So that's one way to think about how our solute molecules keep our solvent molecules, our blue ones, in the liquid phase. The other way to think about it is, again, in terms of entropy, right? So again, remember, nature wants things to be mixed. When our solvent leaves and becomes a gas, it's the only thing up there. Things aren't very mixed at all. So that drive or that a natural tendency towards mixing is really, it's kind of almost going to draw those solvent molecules back into the water to provide more mixing with our solute. So that tendency is going to also decrease the vapor pressure. It's going to remove things from the vapor and put them in the liquid phase. So both of those reasons together work together to lower the vapor pressure when we have a solute present. Note, we haven't even talked about what that solute is. We don't have to know. If it's there, we just need to know how many particles are there, what's its concentration, and then we can talk about it having that same effect. So it doesn't matter whether it's one compound or another. If it's the same concentration, it'll have the same effect on lowering the vapor pressure. Pretty nifty. We can do that mathematically. Right? So all of our colligative properties are going to have reasonably simple, and by simple, I mean formulas like this with kind of just 3 algebraic terms in them. Not a lot, there'll be no squaring and cubing or weird math. There's no natural logs involved here. These are all pretty straightforward relationships. But we do have to be careful identifying what the terms mean. Because especially for vapor pressure, there's two different versions of Raoult's law that tell us how the vapor pressure is being changed. So which one you use depends on which information you have or what information you're trying to calculate. So for a non-volatile solute, okay, so what that means is it's a solute that doesn't have its own vapor pressure. So these are typically our ionic compounds, our molecular solids, those sorts of things. Really just mostly our solids, because they really don't have a vapor pressure. But if we started mixing 2 liquids, they would both have a vapor pressure, and we'd be on the blue side here on a volatile solute. So let's stay on the red side for a little bit with our non-volatile solute. So this is us dissolving some kind of a molecular solid or an ionic compound into our solvent, whatever that is. Doesn't have to be water. It can be other things. All right, so this top one is the relationship that most everyone wrote on their preparation guide when it asked you to write Raoult's law. But the version underneath also works. It's also a valid version of Raoult's law. So it depends on what information you're looking for. But be very careful, right? So some of these terms refer to the solution, some refer to only the solvent, and some refer to the solute. So we need to be careful what information you have in the problem and what information you're solving for. All right. So what it says is that the vapor pressure, so this is the vapor pressure, this is not just for a gas, this is for the vapor pressure over a liquid surface. All right, so this is vapor pressure of the solution is equal to this goofy X thing. Remember, that's our symbol for mole fraction. That's the concentration unit we're going to use for vapor pressure, right? It's going to depend on moles and what fraction of moles are one material or the other. So this is the mole fraction of the solvent, okay? Not the solute, the solvent, all right? Times the vapor pressure of the solvent. And that little zero means in its pure state. So the solvent all by itself, right? It has a particular vapor pressure, right? And we're going to multiply it by the mole fraction, which is always, at most, it can be 1 if it's pure, right? If it's a pure solvent, the mole fraction would be 1, it'd be all solvent, but it's often something less. So it's going to be decreasing. So this will be our new vapor pressure. It'll be something smaller than its original value, its original pure value. Okay. Another version, which may be helpful if you know about the solute mole fraction, is that the change in the vapor pressure, the change in it. So how much did it decrease by? Okay. And this is the information we had on our preparation guide. We had information about how much it went down. Depends on the mole fraction of the solute this time and the pure vapor pressure of the solvent. So again, depending on what kind of information you have access to easily, you may need one or the other of those forms of Raoult's law, right? Our little stars here say that when we have electrolytes, ionic compounds, we're going to have a different number of moles of ions. We're going to have to account for the fact that they've broken up into ions, and we'll deal with that particular little extra thing tomorrow. That'll be a tomorrow thing we deal with, what to do when we have things forming ions. So today we'll focus on non-volatile solutes that are not ionic. If we had a volatile solute, so something that also has a vapor pressure, we're going to treat these in the ideal case as independent things, right? So we'll basically just be doing 2 Raoult's law problems and we'll put them together. So our total vapor pressure is going to be the vapor pressure from each of our 2 components, A and B, whatever they are, but they both have a vapor pressure in this case. So we would use Raoult's law for whatever substance A is and figure out the vapor pressure from just A based on its mole fraction and its pure vapor pressure. And then we'd figure out the vapor pressure for compound B that's in there using its mole fraction and its pure vapor pressure. And then we would combine those 2. All right, so again, this would be in the ideal case. They'll behave independently like that. We'll talk about the deviations again tomorrow. That'll be another tomorrow thing. Okay. So far, so good. Let's take a look at. We'll do an example of each of these. I think we'll only do one today, though. We'll do one today and one tomorrow. All right. So let's. We'll start with the red version. So we have a non-volatile solute. So let's see how that information is given to us and how we might need to extract or manipulate some data that we have to get to our final result there. Okay. All right. So let's make a solution by dissolving 0.45 moles of a solute. Again, doesn't matter what it is, in 75.0 milliliters of water at 50 degrees Celsius. The vapor pressure of the solution is, there we go, is 83.5 torr. Okay, so at 50 decimal point degrees Celsius, the vapor pressure is 83.5 torr. What is the vapor pressure of pure water at 50 decimal point degrees Celsius? All right, so we have to be at the same temperature for our solution in our pure state because vapor pressure does also depend on temperature. Right? We don't want to have to deal with that conversion. So we're at the same temperature, and now we want to know what's the vapor pressure of pure water when the vapor pressure of water with this solute in it has a particular value, 83.5 torr. So we need to pull out the right relationship to use, given that we have a non-volatile solute. We're going to need mole fractions, so we're going to need moles. So we're going to first convert our milliliters of water, right? We have to know what that is in moles, so we can do a mole fraction. So we're off and running with some of our old friends, density and molar mass. All right, so we use our density to get from our volume unit of milliliters into mass units of grams. Right, so the density of water, 1.00 grams per milliliter. And then our molar mass to get from grams to moles. Right? So when we carry that calculation out, we have 4.16 moles of water. All righty, so on to this mole fraction now. That's what we need to do Raoult's law. We need to know the mole fraction of our solvent. So that's going to be the moles of our solvent, water, over the total number of moles. Right? So we've got to add up all the moles of everything in there. And here we are. So 4.16 moles, right? We just calculated that for water, divided by the total moles. So the moles of our water plus the moles of our solute. And we get a fraction, no units. Right? There's no units on mole fraction, 0.903. Right. Now we're almost ready to use Raoult's law finally. And let's make sure we get the right information in the right place. Okay, so here's what we're looking for. The vapor pressure of the solution is equal to the mole fraction of the solvent, which is water, and the times the vapor pressure of the pure solvent, pure water, right? And that's our question, right? That last term, this P with the little 0 for our solvent, is what our question is. What is the vapor pressure of pure water? Right? So that little 0 is representing its pure state there. So that's what our question is. We need to know the mole fraction of our solvent of water. That's what we spent some time calculating up here. And we need to know the vapor pressure of the solution that has this stuff dissolved in it. So what's the vapor pressure of our solution with the solute in it already?
83.5.
Yep, that's our 83.5. This is the vapor pressure of the solution, right? There it is. So, and again, our pressure can be in any units we want as long as it's the same. Right? As long as it matches between the solution and the solvent in the pure state, we can use any unit we want. All right. So now we just got to get things in the right place. So before we do that though, I'm going to ask you, are you expecting the vapor pressure of the pure solvent to be bigger or smaller than 83.5?
Small.
Right. Bigger or smaller? Okay.
Wait, it's bigger because you're dividing the mole fraction, right?
Yes, it's going to be bigger. So the pure version is always the biggest vapor pressure. Remember, the vapor pressure is decreased when we put a solute in there. So the vapor pressure of the solution is going to be smaller than the vapor pressure of the pure, right? A lot of times we think of it the other way. We know the pure and we're trying to figure out the mixture. So here we had the opposite situation. So yeah, the vapor pressure of our pure solvent should be the bigger value. Right, so we can always tell if we've done our algebra upside down there. All right, so here we are, we put our numbers in, right? The vapor pressure of our solution, right? There's pressures everywhere. We have to make sure we attach it to the right variable. So this was our pressure for the solution of the mixed up solution with things in it. Here's our mole fraction of our solvent, our water, right? Not the mole fraction of our solute, but the mole fraction of our water. And then the vapor pressure of our pure solvent. That's what we're looking for. All right, and it does in fact come out to be bigger if we have done the math right. 92.5 torr. All right. All right, so we'll save the longer one where we're combining for a volatile solute for next time. So we'll work on that at the beginning, and then also finish up our other colligative properties there before our exam tomorrow. So we'll take care of all that, and then that'll leave us a whole day to do some review work. I've got some problems that kind of span all of our topics that we can work through. We'll do that on Thursday. So let's take just a few minutes here. Let's try and come back in 3 minutes and bring our problem sets with us, so we can at least spend a little bit of time tonight getting started on that, at least collectively, and then it'll be due tomorrow after we get through the rest of our colligative properties and have a chance to work a few of those problems as well together. Okay, so let's come back in 3 minutes, bring problem set 12, and then we've got a couple of things we have to do in groups for our problem set, and then we'll call it a day. All right, we'll see you back in 3 minutes.
Professor,
Uh-huh.
I have a question. So for the Rolle's law, is the formula N water and plus N solute always gonna be that one? I mean, except for, like, in this case, we're talking about water, but
Right, in this case it's water, right? So it's whatever the solvent is, right? We were finding the mole fraction of the solvent. So for us, it was the moles of the solvent, which was water here, over the total number of moles of everything in there. So solvent, solute, all added up together.
okay. And the N solute is 0.45 moles. So it's
Right.
given.
That was
Or-
given to us in the right units, yes. The water's moles were not given to us, so we had to figure that out.
Okay.
Mhm.
Thank-